That could also be caused by sealing it hot. Are we live?
Good.
You're not rolling now, are you?
You're rolling.
Watch what I said.
Say anything bad about it.
I'm kind of like expanding this a little bit. I just want to, during the break we were talking about edge deletion and should you edge delete or should you not edge delete. Maybe I just want to get into that a little bit. If an IG sits in, like if there's a core weave system and it sits in moisture, so say I got IG, two pieces of glass that are glazed in a sash, and there's not proper drainage. What will happen is there will be corrosion that can start and delaminate the low-E coating and corrode its way from the outside in. This is why if edge deleting sometimes streaks, it's still okay because it stops. It's not really okay, but there can be normally what you see is if you don't edge delete glass, you can get corrosion in an improperly weaved system or drainage system in an IG. But I'm not saying you absolutely need to edge delete your loading glass, but in the world of good, better, best, it is a better insurance policy. Kind of like low TDS water is a better insurance policy. And this is when I took typing class in the 1980s. ASDF is the home position of the left hand. ASDF, angle speed diameter. So that's just an easy way to remember. So what's the deal with the angle? What I mean is normally our, probably it's better to see this. On the overhead here. Angle. What I'm talking about here is the included angle of the cutting wheel itself. How sharp is it, or how blunt is it? Okay. Angle. So right here we can run between, I've seen them as low as 90 degrees, and I've seen them as high as 180, or not 180, but like 160 degrees, about as big as I've seen it. Normally in residential glass fabrication, you're going to hover between 130 to 150-ish, somewhere in there. And we'll get into that in just a little bit. Speed equals force. Faster you go, the less force you need. Diameter. These little Pac-Man guys I drew here. This is the glass surface, and this is a larger diameter wheel, and this is a smaller diameter wheel. A larger diameter wheel has more surface contact or penetration into the glass, and thus a larger diameter wheel is going to need more force to get the desired fissure depth. What I mean by fissure depth is I need this cutting wheel to penetrate into the glass somewhere around maybe like, don't quote me, but maybe around 10% of the glass thickness, somewhere in that area. So for a smaller diameter wheel, it's a sharper bite into the glass and I need less force. There's a couple of pros and cons to this. A smaller diameter wheel for the same linear distance has a lot more revolutions. It's going to wear faster. Than a larger wheel. A larger wheel is not going to be so good at cutting arcs and shapes as a smaller wheel. A smaller diameter wheel is going to go around a tight radius much better. So if you're making something with a 2-inch or a small radius, a large diameter wheel is going to like plow as it goes around and make that turn. So cutting all straights, a larger wheel is better. If you're doing a lot of tight arcs, making those type of IGs, a smaller is better. So that's the difference. And you have to, and if you do a little bit of both, and force. Angle, speed, diameter, force. You want to use as little force as possible to achieve proper fissure depth as possible. Let me just explain how glass is scored and broken. Glass will almost always never, ever break under compression. Glass will always break under tension. When glass is made, if you've ever seen, you could probably YouTube it, glass going in the ribbon, it's red hot, it's molten. It's going through the float line, it's going through the annealing, the cooling, okay? And as glass cools, it makes a compressive shell on the outside. It's like, if you understand how metal is heat treated, you bring it till it's orange hot, and then you quench it, and it makes the outside casing hard. Well, kind of the same thing happens with glass, where you have to, in order to break a score line, you have to drive beyond the compressive layer into the tension layer of the glass. So there's internal stress with the glass. And that's why we need to go a certain depth in, is because if we don't break through the compressive layer, we're never going to get into the tension, and it won't be so easy to break. It'll want to resist breaking. So that's why for thick glass, for instance, we need to go a little bit deeper, because it has a little bit more of a compressive layer on the outside. Okay. Just a little bit of useless trivia for you. Okay? The other thing, and then we're going to get into this, is when we're scoring glass, we're wanting to get the fissure down into the tension layer of the glass. Okay? So you would think that, well, a sharper wheel angle would drive down into the through the glass more readily than a blunt wheel. Here's where that's wrong. And this is where glass is very unique. The energy that is generated during the scoring process primarily reflects at a 90-degree angle to the angle of the surface of the cutting board. So if I have a sharp angle, here I have demonstrated 120 degrees, it's a little bit exaggerated, versus 145, what happens is the energy and the stress is reflected closer to the surface for a sharper wheel than for a blunt wheel. This is why if you press too hard or if you use too sharp of a wheel, you get what's called a hot cut. And it slivers and it pops and it makes noise. I'm going to demonstrate that for you right now. I'm going to take a piece of glass and I'm going to put it up on this overhead. I'm going to make a few cuts. And I'm also going to do something. So I'm going to make a few scores with a hot or a very sharp wheel. This is 127 degree wheel. I'm doing this for later on. I'm using cutting fluid. Put this on the overhead. Just let this simmer for a little while. Actually didn't like that. I'm trying to make a really hot cut. We're going to do an edit here. You guys hear this?
Oh, yeah.
This is much more demonstrative of what I'm getting at. So if you have this in mind, see this little hatched area versus this, and you imagine what's happening here. So what's happening is I'm driving the energy down into the glass, but it's shooting out the sides. And for a more blunt wheel, it's driving more of that energy straight down instead of out. That's why I need a more blunt wheel for thicker glass, because I need to drive down deeper, okay? That's the whole, it's like counterintuitive, it's the opposite of what you think. But that's the dynamic of glass, and the reason for that, and why I explained the compressive and the tension layer of glass, that's what's going on. We got to get into the tension layer to be able to break glass. So, does that all make sense? Pretty fundamental. I've got 4 different cutting tools. I've got a 127, a 135, a 145, and a 155. Meaning, you know what that means now? That's the angle, that's the included angle. You have a piece of 5 mil glass in front of you. What I would like you to do is just each take one of these, but first, let me explain how to cut glass. This one's actually okay. You want to hold the tool. The professionals say hold it like this, between your first 2 fingers. I can't do that. I hold it like a pencil. What that does is that makes it vulnerable to tilting. So if I tilt the tool, what have I done to the angle? I've made it sharp and blunt on the same one. So you want to make sure that you're completely vertical. It's very important. You want to start close. You never want to start off the glass and on. You just made a defect. You want to start very close to the edge of the glass. Go with consistent speed and pressure or force down. Have the tool as, see how the tool has an angle on it? You don't want to be like this. You want to be like this. You want to be at about a 45-degree angle. And you want to run all the way up the glass. You don't want to stop short. This is why we have a bit of carpeting right here. So watch what I'm doing. Okay? I run right off into the glass. Okay? And what I want you to do is 2 or 3 or 4 cuts. So the red one is 127. Yellow is 135. Charlie. Green one is 145, and purple is 155. So I want you to just start at the top and go to the bottom and make a few scores. You did? You're stopping short. Run it all the way up. Yep. I don't have a problem if you hold it like a pencil, as long as you are cognizant to keep it straight. If that's more comfortable. Okay, so are you able to hear it, feel it? So Tom, look at yours.
Shards everywhere.
Good Lord. So you've got the 127.
Yeah.
instantly I would say, oh my gosh, you're either pressing incredibly too hard or you have the wrong diameter wheel. Okay, so there you go. There's your first assessment of failure. Check this out. And it just keeps stress relieving. Look at this. And if you watch it, it's just,
It was still popping when you were picking it up.
it's still popping. It's like, it's relaxing. So we'll talk about this later, but it takes time. Glass is almost like a fluid. So that's a really good example of what not to do, Tom.
Good job, Tom.
It's not trade, so you've got the hot one. Let's get new pieces of glass.
Yeah.
Put that aside. Just make a little pile. And now trade the wheel. Maybe just go down. We're gonna do this 4 times. And just make some scores and understand what you had and what you have now. So Steve, is that a lot different?
Hey. Sounds
I didn't get too close to the edge on that one.
Okay, now trade tools. Move it down. Bring it on down.
Same piece of glass.
Sure.
Could they turn it over?
No.
No.
Wow.
What do you have? You have the 135. Does that feel pretty good, or is that's still pretty hot?
It feels hotter than the green one did.
Because you're using a 135, and you were using a 145.
Okay.
10 degrees difference, and you're like, whoa, that's a big difference. So, okay. Now you get to do it one more time. Notice a big difference, Ken? Yeah, now you're creating all kinds of Rice Krispies. It's a hot, super hot cup. And that's terrible. I'll show you why that's terrible in just a minute. Because that is going to relate to incredibly bad edge quality, breakout quality. Okay? All I'm hearing right now is a bunch of snapping and popping and stress relieving on this glass. It's pretty amazing. Okay. So now take your glass, put it up inside again. What wheel do you think is going to be the right one?
That's the purple one.
Purple?
Yep.
All right.
Which one was that?
That's the 150.
So now I'm gonna, all right. So now we're gonna break it out. We're gonna start to take a look at what the effect is of your score line, okay? So same as you did before. Maybe give yourself an inch or so because I'm gonna show you how to break this out, and then we're gonna look at the edges. Okay? So start here. Run off. And I didn't make a lot of, you almost shouldn't be able to see. Now I'm going to take my fingers, curl them around like this, like fonts, and make a fulcrum out of my fingers, and then peel the glass. Okay? So I'm going to start here. Put that score line in tension and get it to run to the end. I'm not going to see this a lot. Go here and go. All right, that's terrible. You don't ever want to edge break like that. You want to run that score from one side to the other. The way you do that is and this is why you need to run this off the edge, is because you need a starting point. If you stop short, you'll never get that to run. So I've just done that. It didn't take a lot. So let's see if you guys can do that.
So what's
It was pretty easy for me. Why are you guys? Oh, he did it.
Oh, okay.
Try it again. See if it's beginner's luck. Not bad.
There we go.
Maybe it wasn't beginner's luck. You're, Ken, on the way to determining that this is probably not a good tool for this thickness of glass.
I agree.
So now, let's just trade tools and try and break out. Hope you guys are keeping track of what works and what doesn't work.
Yeah, which one were you using down here?
Yellow one.
Yellow, okay.
Yeah, you can use this piece of glass.
Use a different piece?
No, use the same one if you can. Oh boy, it sounds terrible, doesn't it? Like a cat scratching a chalkboard.
Okay, I was gonna be only one.
No.
Better.
You got it, yeah.
If you've got a grunt when you're breaking out a piece of residential glass,
Yes.
you know something wrong.
No, no, yeah.
All right, try another piece. Or move it on down the line.
That was, you had just used the purple one, which somebody mentioned you might try that one. Ah!
No.
Nope.
All right, let me give you a pro tip. Do the same thing, but press a lot lighter. Press lighter. I'm watching you push down, and you're
On the cutter.
on the tool itself. Push down less.
You're supposed to try to use the same amount of force with each
Nope.
cutting tool. Okay.
You see all this on that chain?
Oh, I saw some charts flying.
I'm not sure if it broke out any easier.
Switch it again?
Yeah.
How'd that run with her?
Not well.
Terrible.
You're back at green or you back to
This is the last round.
Ooh, ah.
Much easier.
Green's better than purple.
Green's the winner. What's green? 145. You didn't have to press hard. You didn't make a lot of chalk. It's not a hot cut and it broke easy. So now, interesting. Would you guys say that the red one was terrible?
Yes.
I agree. Would you say the purple one was good or bad?
That, purple was the first.
Sounded better than.
So now, this was a purple one, Kevin? So now, be careful to now take this jeweler's loop, put it up to the edge, and you can start to get a little finer in your analysis rather than a feel. You can quantify the fissure depth if you have maybe a scale on that jeweler's loop. Again, you want to go a certain depth, you want to maintain that consistency. get into the tension layer, which is about 10% of the glass thickness. Okay?
So, when you said I was custom design, I would have seen that, I would have been able to see the depth change.
So if you see that there's a little bit of chatter and then it gets smooth, that's your fissure depth. Or what I hope is smooth. If you press too hard, if you're using the wrong wheel, diameter-wise, you're going to start to create shark's teeth, hackle. We've got a poster over there that shows some of the poor edge quality. If you're using a dull wheel, you have to press harder. And what I said at the beginning was, you want to use as little force as possible to achieve a good score. And good breakout.
Why do I care about the edges?
What's that?
Why do I care about edge quality?
Why you care about edge quality? Why edge quality is really important. It's almost like you are a plant. That's going right to that. Poor edge quality is going to relate and result in increased thermal stress breakage or glazing breakage. So if you beat the glazing bead in and the IG runs from the edge, there was a stress concentration on the edge of the glass. Glass normally doesn't break from the middle. You can't break glass. You can throw a baseball through it, but you've broken through the compressive layer into the tension. Glass will only break the tension. You could put 10 elephants on this glass and stand on it, and it's not going to break. But if you put a little tiny stress concentration in that edge, and then you beat a glazing bead around the edge, it's going to run from the edge in, because you've created a stress concentration big enough to get into the tension layer. And it makes it very easy to break. So all we're doing with the cutting tool is we're creating a controlled defect. And we want the brake to run along our defect. If it runs off, that means something is wrong with force, wheel diameter, or something of that sort. Or if you're using excessive force or you got the wrong wheel, you're going to create this chalking, this hot cut, and it's going to result in a harder breakout. So now what I want you to do is take the sharpest wheel, press hard, break it out, and look at it with the jeweler and see what you see. So let me give you get low on left. Use your so take the red one, make a score line. Look at the red and break it out, and then pass it down and then evaluate. Press hard. Okay. Now break that out and evaluate the edge quality.
I went too far the other way.
You see how it's jagged? So you're using the wrong wheel.
This.
Yeah, you can just tell eyeball.
You can, so you used the wrong wheel angle and you pressed excessively hard and you made sharp teeth. You made a super hot cut and you don't need a jeweler's loupe to see that that's very jagged. So if you see these in the IG card, you're like, oh man. I think those have a good chance of surviving. Because this unit might get out into the field and it's going to be okay until wintertime, until there's thermal contraction or thermal expansion. Maybe in the summertime, you're going to start stressing that edge. 2 years after that install date, it could run. And it's like, why? And then if forensically you take a look at that IG and you see edge quality like that, you're like, okay. They might not have changed their wheel for 2 weeks. You know? They were just like hammering, like really.
So if you were using the wrong wheel, and if you were using the same like amount of pressure, and it wouldn't break out, and you add more pressure so you can break out, you're going to see issues like that.
Yeah. All right. So now we've done a lot of work with 5mm glass. So push push all that to the side. I got some pretty common 2.5 mil. We call it single strip glass, but it's 2.5 mil glass. This is half this thick is what you've been working on today. And what you do is use the purple wheel. So for thick glass, I had you using a sharp wheel angle. Now for thin glass, I want you to use a blunt wheel. So do the same thing. Like what gives? See if you can break that out. I bet you can. So visually, you can look at that and you see a lot of jagged. It's not very smooth, is it?
Oh,
It's awful. It's terrible. I can tell by listening to
Yeah,
that
okay,
band.
when you listen to it.
All right, so now take the. Look what you did. Broke it. Steve, what you did is you slowed down at the end. That had nothing to do with the tool, but you want to run it off nice and quick. So now take the green one. And it sounds terrible. You should almost not hear it break.
It's like resisting.
So who's got the green one? Right here. All right, so do the same thing, right? Slow that down and with the green one. See how that's a little bit white? I might challenge that here. Whoa.
Whoa! Like,
Whoa.
wow.
Like basically fell apart.
Yep.
Yowzers. So that was the difference between, here's what's weird, a 155 and a 145. 10 degrees difference was all the world with 2.5 mil glass. I might like to say that a 138 or 140 might even be better, but if you're processing 2.5 and 3 and 4 mil on the same thing, 130 or 145 is pretty good. Usually where I start on glass cutting machines with a 145, and if for whatever reason it's not happy, I might go down or up from there. So, does that make sense? Anybody want to practice a little bit? Like, okay, 145 is pretty good. What about 130?
145 is the green, right?
145 is green.
Yellow's the 135?
Yeah. And maybe once you do that, that broke out nice, but you see the little slivers? It kind of made a hot cut. So if you were doing that again, I would hit it lighter, press lighter. Is that what the 145 Tom?
No, that was with the one. I didn't
Yeah.
press this hard.
Yeah, 135 isn't bad. That looked pretty good, Charlie, because I don't see chalking. But I don't know if it was as good as 145. It might be. There's a certain range where you're okay, and then it just goes terrible. Okay. Here's the deal with 2.5 mil glass, and it's different. It's really thin glass, and when I said it goes through the float line, it doesn't take as long for it to cool or anneal, cool down, as it does for thicker glass. So 2.5 mil glass cools quicker. It quenches quicker, and thus it more quickly builds a thicker compressive layer than 3 mil, 4 mil, 5 mil. So that's why 2.5 mil might be good to use the same wheel diameter as a 3 mil. But then you get into 4 and 5 mil, and you start to get into, hey, this is getting a little bit bad. So 2.5 mil has a relatively thicker compressive layer than 3 mil, proportionally to the thickness of the glass, okay? Because it's thinner and it doesn't have so much of a heat sink to hold the heat, so it cools down a little bit quicker. So that's some of the, like, why is 2.5 work just as good as 3 with the same wheel? Because it's just a little bit of mass stress dynamic going on. Okay, you guys want to play around with cutting stuff anymore, or we move on? You guys get it? 155 is terrible, 127 is terrible. In all cases, for 5 mil glass and 2.5 mil glass. So without even a machine, you can start to understand what would be a good baseline or a starting point. Okay? And you could do things like, if you wanted to understand, you know, there's optical comparators, there's all kinds of tools. If you wanted to understand, well, okay, you'll set 10% of the thickness. You could make a score line, then flip it over. Make a cross score line. And now I could take and I could actually measure the fissure depth. This is really difficult to see, but there's no way. But with the jeweler's loop, take a look at that, and you could start to see where the stresses are blooming in that score line. Be careful, because it's going to want to break.
Yeah.
But you can see a little balloon
Oh, yep.
around that. You could see the fissure depth. Yeah, just hold the bottom or else it'll break in half. It's very fragile. So you could see the fissure depth. You can measure that and say, all right, did I go too far? I pressed too hard. It's going to put it, it's going to crush it. This is something you can't do on a machine. You can't check that, but you
Right.
could definitely look at the edge on an optical comparator with the jeweler to get a good idea of how deep you're penetrating. Right? And force-wise, you want to be like, if you're more than, like for this glass, single strength glass, if you're more than like 8 pounds or 6 pounds, you're pushing too hard. Right? You're using the wrong wheel or you're pushing too hard. Okay? And then it goes up from there. So the thicker glass, you need 15, 20 pounds of force, maybe a little bit more for the really thick stuff. And then you get into the really thick stuff, and you might need brake assist. So clamp or pliers, like tile cutters, where they've got the tile breakers, where they've got the bead, where you need to, you need to put that edge into stress. But on the 3/4 and plate glass, you sometimes need clamps and tools to break that. But for what we're doing with residential and IG, typically that's the case. Interesting, eh? So the last thing I want to cover with you guys, I got a few more things, but the importance of cutting fluid. What's the deal with cutting fluid? Everything we've done, you can hear and see chalkiness, hot cuts, blooming. Cutting fluid does two things, primarily. Number one, it lubricates the axle and the wheel, and it probably by a factor of 90+% increases the wheel life. If you're running dry, expect to change your wheels very frequently. So it basically is a lubrication for the mechanics of all the friction and everything that's going on. The second thing it does, most importantly, is it pushes cutting fluid into the fissure depth, into the fissure, and prevents the glass from healing. And by healing, I mean if you store glass and you run it out on the breakout table, let it sit there for over lunch or overnight, and you come back in the morning, you will not be able to break that piece of glass. So the stresses that you see here, all of this hot cuts are stresses that were not able to be held into the glass. They release themselves between the compressive and the tension layer of the glass. They just pop. But ideally, you want to hold those stresses in the glass, in the fissure, such that when it comes out onto the breakout table, it breaks very cleanly and nicely. If you score glass and you let it set for a while, you'll see it and you hear it relieving itself. All we want the cutting fluid to do is hold the energy into that fissure where it is until you break it out. Because over time what happens is it starts to disperse. All that energy starts to disperse and you lose the effectivity of making a nice break. And you're going to get crappy edge quality. You're going to get very poor edge quality if you wait too long. Or if your cutting fluid does not have that evaporative rate that is desired for the throughput rates that you have. So there's, I don't know, a whole bunch of different types of cutting fluid that have different rates of evaporation. Some evaporate very quickly, in a matter of seconds. Some take minutes, some take a very long time to evaporate. So you want to make sure that the cutting fluid that you're using is, number one, water soluble. Don't use kerosene, don't use olive oil, don't use any of this stuff. It's the depth of the edge adhesion to use inorganic or oil solvent-based cutting fluids. Never use a solvent-based cutting fluid. Always use a water-based or water, meaning that the washer can break it down easily. Okay? But you want the evaporative rate such that that fissure is held for the amount of time you need to break that out. That's all it does. So here's the difference between these four scores on this side were done dry. I dipped my tool into the cutting fluid and did these four. You see the difference? It held the stress long enough where it didn't flake out. So it basically masked the hot cut. So all cutting fluid does is make a good cut. It makes a cut, improves cut quality or breakout quality. It doesn't tell you whether it shouldn't be used to mask improper setup or improper selection of the wheel. But it does hold those stresses. It's very important. So basically, imagine the crater. There's a V being put in the glass. We're just filling that. We're pushing it hydraulically, the cutting fluid into there. And we're holding it from rebounding. Healing, I call it. Okay? So that's what's going on here, is we held that score. We held those stresses. And that's the most important thing that cutting fluid can do. When you're using cutting fluid, not if you're using cutting fluid, you only want as little as possible to be used on adjacent to the score line. You only want 1 or 2 millimeter of fluid to be beyond the edge of the score line. So let me show you this one. So you see this pooling. You want just a little bit of pooling, 1 or 2 millimeter on either side of that score line. If you're like this can bloom out into the low E surface. It could stain. You could get some iridescent staining going on if the coating is sensitive to that. So you want to be careful, especially for these low E and coated glasses, etc. And you'll notice over time that this is going to flow out a little bit. So it's a touchy adjustment. You want to make sure. I always like to say the enemy of enough is more. Oh, put more cutting fluid on, it's going to make better quality. All that's going to do is put more contaminants on your glass surface. Like I explained at the beginning, you're not going to be able to detect it in the wash water. You're just going to transfer residual contaminants into the washer. But it is an incredibly beneficial and useful product to use in glass cutting standard. And there are a lot of wrong materials in these. Make sure you're using the right material. Okay. The only other thing I wanted to mention was carpeting. The importance of carpeting. So maybe push that glass aside. And once you do that, don't touch the glass anymore, but take your gloves off. You'll see there's a lot of glistening in that carpeting. That's glass that, if it becomes trapped or embedded into the carpeting, can scratch glass as it's floated or transferred along. Mostly this is a visual quality issue, but scratched glass is as big of a failure as a seal coat. Okay? So how do you get rid of these glass shards? If the carpet is piled or it's like a looser weave, there'll be more chance for fragments and shards to stick in that can't be vacuumed out. I never recommend blowing it with an air gun because it just blows. During the break we were talking about edge deletion and should you edge delete or should you not edge delete. Maybe I just want to get into that a little bit. If an IG sits in, like if there's a 4-weave system and it sits in moisture, so say I got IG, 2 pieces of glass that are glazed in a sash, and there's not proper drainage. What will happen is there will be corrosion that can start and delaminate the low-E coating and corrode its way from the outside in. This is why if edge deleting sometimes streaks, it's still okay because it stops. It's not really okay, but there can be normally what you see is if you don't edge delete glass, you can get corrosion in an improperly weaved system or drainage system in an IG. But I'm not saying you absolutely need to edge delete your loading glass, but in the world of good, better, best, it is a better insurance policy. Kind of like low TDS water is a better insurance policy. Detergent, all these factors are put you either at an advantage or a disadvantage, where if you do this wrong, you have to do these other 3 things more right to make a good IG, okay? So it just increases your odds of success, some of these things I'm talking about. But not totally, I'm not saying anything's absolute.